before we dive into drawing diagrams and doing science, let's identify some key principles to keep in mind. Okay, number one is going to be this one is a tricky one to spell. Aufbau principle, which simply states place one electron at a time at lowest energy. Okay, that's the Aufbau principle. Now we have Paul exclusion. So we're just going to move that down a bit so it's clear that they're different. There can be a max of 2 electrons in an orbital. And they must have different spins. Okay, and then finally we're going to have Hundred. Okay, so what this states is maximize unpaired in a sublevel. All right, well, that's nice. What does that mean even? Well, let's find out. So let's say we have a carbon atom. From the periodic table, we know that its atomic number is 6. We're going to say it's neutral, so that tells us that there's going to be 6 electrons. And so if you remember from our table, you can go back and look at it if you want. We have first a 1s orbital, which can fit 2 electrons. And then we're going to have a 2s orbital, because that's the next lowest energy. And then finally, we're going to have a 2p orbital. Right? So lowest, next lowest, third lowest. So now we're going to place 1 electron at a time, starting with the lowest energy. Okay. And before we move on, though, we know that the 1s is still lower than 2s, so we're going to pop in our second electron there. Okay, so that's 2 out of 6. Do the same thing here, that gets us 3, 4. And then in our 2p orbital, it may be tempting to do both of them like this and say, look, we satisfy the first 2 principles, great. But Hund's rule comes in and says, no, you don't have 2 electrons like that. Rather, you're going to have 2 electrons with the same spin in 2 different orbitals. And so each one of these lines is an orbital, and the energy level, primary energy level, and then sublevel are the letters, number and letter underneath it. So 1s orbital, 2s orbital, 2p, first orbital, second orbital, third orbital. Okay? Cool. So let's go ahead and do one more quick example. We're going to do germanium. Okay. So we know we're going to have the 1s, 2s, and 2p orbitals. And we'll go back to the 3s orbital. And then we'll do the 3p, and then we'll wrap around down here. So as you remember, or as we showed on this table, the 3 sublevel, the 3 primary energy level, has 3 different sublevels, right? You have the S, you have the P, and then you have the D. So it may be tempting to say, well, 3D is obviously the lowest energy, so we're going to stick it right here. Problem is that the 4S, or primary energy level 4, S orbital, is actually lower energy. So we're going to put that first. And then this is going to be followed by the 3D. So that's going to give us 5 orbitals. Okay, and then our 4p. Okay, so germanium, we know that our 1s is full, 2s is full. So we're just going along, filling in the electrons until we hit the necessary number. And see here, 4p. So because when we hit the 4p, we only have 2 electrons left. We're going to separate them out just like we did with carbon. And so you'll see that carbon only had 2 in the 2p. Germanium has more electrons in its core, but within the 4p orbital, we see that it only has 2 again. And so it's going to have some similar properties to carbon. And yeah, so this is actually going to be atomic number 32. And that's where we got the 32 electrons. So the first 30 electrons are used up filling everything to the 3D fully, and then the last 2 are used for the 4p. Okay. Now, what if we wanted to write this as an electron configuration or shorthand? Well, what we do is we take our energy levels and then just say how many electrons are in each. So you'd have the 1s2, or 1s energy levels, 2 electrons there, and then 2s2. Okay. 2p6, 3s2, 3p6, 4s2, 3d10, 4p2. So as you can tell, this is a lot faster than drawing out all the different orbitals. Okay, so this is all nice and good, but you'll notice that the 1s to the 3p6, they're all full, right? It's only once we hit the 4s that it's no longer full. So what we can do is we can abbreviate this using the elements on the last column of the periodic table. So for this particular one, it's going to be argon. And so we can say that the electron configuration here, with all these numbers, is the same as saying electron configuration for argon, followed by 4s2, 3d10, 4p2. Okay? So what we did is essentially said from here to here, that's the exact same as argon, or the last element in the periodic table on the row just above the row of germanium. And then we continue on with what's left over. So once we've hit argon, then we wrap around the periodic table again and start over and say, okay, from argon onwards, we're just filling these 3 energy levels. Okay? So this is a nice little shortcut you can use. You don't have to. If you prefer, you can go ahead and write it all out like this, or do this way even. But this way is significantly faster and allows you to become more familiar with the periodic table. But enough rambling. Let's go ahead and do some problems. All right. So how do we find out number of protons, neutrons, and electrons in the following? All right, so the ones we have chosen as our guinea pigs are going to be aluminum. That has, and we're also going to do boron, which has an atomic number of 35. Okay, great. And then while you're working on that, I'm just going to write something on the other side of the board quickly. Alrighty, so diving back over here, number of protons is going to be our atomic number, so 13. Number of neutrons is going to be mass number minus atomic number. The number of electrons, because it's 3 plus, is going to be 13 minus positive 3. This electrons. Similarly for bromine, protons is 35. Neutrons. And then our electrons is going to be 35 minus a negative 1. So there's 36 electrons. Okay. All right, so you should have already had a chance to work through this as well. If you haven't, go ahead and hit pause. Ignore those two. All right, so sodium. We see that, well, actually, I should have put the atomic number. So chlorine has an atomic number of 17. So that tells us how many, excuse me, whereas sodium has an atomic number of 11. So that tells us how many electrons they are, because they're neutral atoms currently. So if we have 11 electrons there, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 electrons. Okay. So then when we're writing out our electron configuration, 1s2, 2s2, 2p6, 3s1. Okay. Nice electron configuration. And then here we're going to have, and do the diagram first. So we're going to have 2 electrons there, 2 there, 2 there, 2 there, 2 there. So now we have 7 electrons left. Well, that's clearly not right. We better change that. Have to have opposite spins. So there we go. That takes us all the way up to 12. So we have 5 left. That's 1, 2, 3, 4, 5. Okay. Okay. So that's our electronic configuration.